Hi, I'm Dr. Bob. Today I'm going to do one of my non-traditional videos. I don't really have a format for this video, but what I want to talk about are some of the ideas behind my book, The Theory of the Time-Energy Relationship. Here it is right here. This is a book that I wrote back in 1995. I published it, and I had an idea in my head. And I vexed over this idea since, literally, since childhood. I wonder who hasn't looked up into the sky at night and seen, all the stars and wondered where the end of that is. More importantly, what's at the end of space? What is out at the edge of space? What is beyond space? What's out there? What's out there beyond our perception? What's out there beyond? Is it just plain, pure nothingness? As a child, I imagined there might be a wall out there, right? A big old brick wall. Oh, that's the end of space. There's something that stops. But, of course, that begs the next question, what's on the other side of the wall? Well, more space, of course. And so I retched over this question all my life. And I had theories, I had ideas, I even took up physics as a goal in my life, to get a PhD in physics, which I never did get. I got my PhD in electrical engineering. In essence, I'm an engineer. I'm an engineer by psyche, by thought, by trade, by this is what I do. But I'm also a scientist. And the scientist forces me to ask questions and to find answers to them. And it dawned on me one day as I tried to understand the nature of the universe that what really came to me while I was sitting by a lake. I had come to the end of my rope. I said, I have no clue how to resolve this question, how to solve this problem. And I was sitting there at the lake, and I was just retching, what is space? What is it? And it just occurred to me, and I had this revelation: empty space is just that. It's empty. It's space. And how do you quantify that whole idea? Space is actually nothingness. It is that which does not exist. Space does not exist. That is getting a hold of that concept isn't a simple thing. If you take the idea of three-dimensional space that we understand, and then of course put it in a time frame called four-dimensional, as Albert Einstein liked to do, thinking of space four-dimensional. Of course, we can all do that to some degree, visualize three-dimensional space and then visualize that space in motion. We have four-dimensional space. But once you take space out of the whole equation, out of the whole question of physics, of the nature of the universe, then you come to a revelation that these are things that don't exist. And if space does not exist, what is left of science is that which does exist. And one thing that we're pretty sure that exists is time. Here is yet another perception. We perceive space, we perceive time as something that advances, that it only goes one direction. We assume this through the laws of entropy, that there is only one direction to time. And of course, space has three dimensions. So how do we resolve of course, the question of existence, the very question of existence? How did everything in the universe come into being? And so we try to answer that question in many ways. We have some Big Bang theories. We have these other theories about the M theory, which, as I recall, I believe the M theory is membrane, but other scientists have some other ideas about it, because the end theory has, well, I'm not going to talk about end theory right now. What we want to talk about is the idea of space as an acting causality. And I believe that because scientists may have come to terms with the idea that the ether does not exist, because even after Einstein said that, came up with the theory of relativity and talked about the ether, and then Michelson and Morley came back and said, well, let's prove that the ether exists. And they did this experiment, and they showed, instead of proving that the ether existed, they showed that the ether doesn't exist. There's no such thing as something that occupies all of space, because anything that occupies all of space would have infinite density and, of course, infinite mass. So you couldn't move anything through space. Space became just that, empty space, but so many scientists were still attached to the idea of the ether. And even today, they fill space with this new material. Instead of ether, now it's called quantum foam. All right, well, you know, space is just that. It's empty space. You want to fill all the space with quantum anything, and you're trying to move something through it at the speed of light, there's stuff in the way. The fact of the matter is that, well, I want to say what the fact of the matter is. The theory of the matter is there's some sort of quantum space, quantum foam that occupies all space. And my theory is, no, empty space is just that, empty space. There might be some quantum foam near matter, especially very close to matter, which makes matter act in very quantum manners, in very quantum ways. Now, and this, of course, is one of the great paradoxes of our existence. They give this thing called mass to matter, okay? And one of the things that can help you overcome the idea, the notion that space actually exists as an acting causality in the universe. This is the very important point, because what this says is that space is an acting causality. What I'm saying is space is not an acting causality. And there's one simple thing that you can do, one simple mind experiment that you can do. And I know that many physicists will talk about my theory and say, well, that sounds a little bit more like philosophy than anything else. And no, I haven't done the mathematics behind it. No, I haven't. But here's, yes, philosophy is, let's take an atom, right? Let's say you want to know the mass of something, right? Let's take a big giant ball of lead, and it's one about this size is going to be really heavy, like 200 pounds maybe. I mean, it's lead. Lead's heavy. Lead is heavy. That's really dense material. But if you'd taken that, just one atom of lead apart, and you zoom in on it, and you make it, let's say, the size of the solar system. Well, not even that big. Let's make it the size of a football stadium. And we don't have to take a lead atom. We could take something like a hydrogen atom. And we'll talk about just that's one proton and one electron. And if you had a hydrogen atom the size of, say, the Houston Astrodome, and I don't even know if that exists anymore, I think it might have come down, you would have the proton at the center of the atom, say about the size of a silver dollar, and the electron spinning around this thing at unrealizable speeds, ridiculous velocities, out in the outer sections of the astrodome. The vast majority of the hydrogen atom would be, you guessed it, empty space. The same thing, of course, is true of any matter that we have, any sort of atoms we have. The hydrogen atom is the size of the astrodome. A lead atom is going to be, I don't know, 50 times, 100 times bigger. And it's still going to be mostly empty space. close to, I don't know, I don't have a number, I can calculate it, 99.99999999999 something percent empty space. This is true of all atoms. This is true of lead. This is true of gold. This is true of air. This is true of any atom you can think of. And then if you go out into space where there are no atoms, it's more than that. It's a lot of empty space in the universe. So what's the rest of this stuff? Okay, now the next question is, how do you get something called mass? Well, mass has a definition. It has volume and it has density. Okay? I think the formula is mass equals volume times density. In fact, that's pretty close. That's the equation. So let's go down a little further. Let's take it down to an electron. That's a pretty small particle. Let's say I have an electron this big, and it has some mass. And of course, we can figure out what the density of air is. We can figure out the density of lead. We have a ball of lead. We can figure out the volume is 4/3 pi r cubed times the density, 100 kilograms per cubic, you know, whatever. And then here's the mass. So, and then we calculate that. But how do you calculate the mass of an electron? Well, we know we have. It's made up through the energy. We use Einstein's equation, equal mc squared. We know that the mass of the electron is 0.511 eV. That's the energy of the electron. The mass is something just tiny, really tiny. But let's go back to the mass equals the volume times the density. All right, well, you know, when we use the idea of a density, here's electron. When we get a picture of an electron in our heads, almost every one of us gets a picture of a little ball, right? And this ball has some volume, it's this size, and it has this much density. What does that say about it being at the space inside the ball? If it has density, that means there has to be some empty space inside of that ball. Here we go again. We've got some empty space inside this ball. We've got a physical picture of an electron. Now I'm going to take a break here. Thanks for watching my program.